Hello and welcome to Ode's Reintroduction to Programming, Chapter 2. In Chapter 1, we looked at memory and instructions and how these form the foundation of computer programming. In this chapter, we're going to ask, how do we go from instructions operating on memory to a recognizable programming language? We'll be looking at a variety of languages and the techniques that make them possible. We're going to start with regular expressions, partly because they're cool, but also because they'll provide some useful groundwork for getting into parsing later on. You may be thinking that regex is going to be pretty complicated, but actually, I've come to believe that it's more complicated to write regular expressions than to understand how they work. My hope is that you'll end this video with a feeling something like this. That doesn't look so difficult. I'm sure I could have a go at implementing something like that. Maybe I'll give it a try. In case you've never heard of regexes before, here's a quick intro. Regex is a special purpose language used to recognize patterns within text. They're often used in find and replace in text editors. For example, if you wanted to find all of the hex numbers in a file that started with 0x, you could write a regex like this and it would recognize all of the parts of the string that fit that pattern. You can see that this one isn't quite right. It probably needs a little bit of tweaking, and that's quite a common experience when it comes to writing regular expressions. Regexes are a nice example of a simple programming language. When computers became available, programmers wrote in machine codes and assembly language since that was all that was available. But before long, they began to see the opportunity to create programming languages that the computer itself would translate down into running machine code. We saw in the Stacks video that one of the big ideas they had was to get computers to process normal, everyday arithmetical expressions. We can consider everyday arithmetical expressions as a kind of abstract system with its own entities and rules that would exist whether we invented computers or not. But when we did invent computers, we were then able to get the computers to follow those rules and simulate that abstract system, get it to do useful work for us. But everyday arithmetical expressions are just one example of an abstract system. There are other kinds, and they can do other things. Many great advances in the world of computing came when somebody took an abstract idea from mathematics, an idea that could do useful work, and found a way to simulate it using computers. And one of those ideas was finite automata. This is a finite automata. It has a finite number of states connected with transitions. They're also known by some other names like finite state machines or just state machines, though the term state machine typically implies we're talking more about a concrete implementation than an abstract example. So we'll use the term finite automata for now. You may also recognize these as a type of graph, that is, nodes connected by edges. This is a finite automata that I've designed for recognizing the word ha. H-A-H. We can use it by deciding that one state is the start, that'll be S1, and one state will be the success state, S4. Then we can go through a string, character by character, following the transition that matches the letter we see. If when we get to the end of the string a success state is active, the string matches. If anything else happens, let's say we meet a character that there's no transition for, or we end the string and we're not on a success state, then the string isn't a match. Those additional rules aren't essential to what a finite automata is, they're just a thing we're layering on top of it. For example, if you wanted to use the same finite automata to find matches inside a string rather than just detect whether a string was a match, you would use it in a different way. For example, you might not care whether you hit the success state at the last character or at some character earlier on. But for our purposes, we'll look at matching the whole string. Let's look at another example. This finite automata is designed to match HAH and HEH, but not HUH. It does this by giving the second state two possible transitions, one to A and one to E. These then join back with an H to the final state. This is the beginnings of how we can use finite automata to recognize patterns. It's loosely equivalent to this regular expression here. If you're not super familiar with regular expressions, or regex, or regex if you like, then basically what they do is they recognize strings according to a pattern. This one is saying to recognize strings starting with the letter H, then either an A or an E, and then another H. That vertical bar means OR, and the brackets are used to control the scope of that OR. Here's another example that recognizes LOL or LOOOOL with however many O's you like. It starts at S1, takes an L, then an O, and then it can either take another L or it can take an O and loop back on itself to the same state. This configuration allows us to recognize sequences of varied length and is roughly equivalent to this regex, where the plus sign means match one or more of the previous item. This, along with all of the finite automata we've seen so far, is a particular kind of finite automata called a deterministic finite automata, or DFA. That means that each state can only go to one other state given a particular input. So S3, if it sees an O, can only go to S3. If it sees an L, it can only go to S4. It might seem strange that we'd ever need a word for this. As software engineers, we might think that non-determinism is always to be avoided. But non-determinism can be pretty useful. So let's look at an example of a non-deterministic finite automata, or NDFA or NFA. This finite automata recognizes laughs which start with an H, then one or more A's, then an H, and then one or more A's, and repeating that sequence indefinitely, but always ending on an AH. So it's ha 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 style laughs, along with as many A's as you like, but no double H's, and always starting and ending with an H, if that makes sense. This finite automata is non-deterministic because S3, given an H, can go to either S2 or S4. So what do? Can you feel your heart burning? Can you feel the struggle within? As a software engineer, this troubles me. I know computers are deterministic, and this is going to perform a sequential operation, just because that's what it's running on. So what does it do? You might not feel anything like the level of discomfort I feel, but if you do, then pay attention to that feeling. It's the feeling of a software engineer trying to understand a mathematical idea, and it's at the root of a lot of the creative tension between mathematics and computing. It's perhaps the same tension that made the Algol committee so against recursion, and on the other side made Dijkstra see what others couldn't. So store that feeling away in your memory, and when you feel it again, get curious. Mathematicians can do all kinds of wild stuff with their ideas that allow them to take conceptual leaps that as programmers sometimes we miss, so it can be very useful. Anyway, so what do we do with this situation? This is an abstract mathematical idea, not a computer program, so we can follow whatever rules we like. In fact, one of the papers I read, which was written by a guy called Russ Cox, has a fantastic line in it. It goes, quote, "In this situation, it turns out to be interesting to let the machine always guess correctly." By which he means to let the state machine guess whatever choice will result in a successful match. And I'm like, what are you talking about? It turns out to be interesting. You can't just have the rules be it just guesses right. That doesn't make any sense. At least that's what my intuition says. He can do what he likes, and in fact, he does, and you'll see why it's useful. So what you do in this situation is a little controversial. There are different choices you can make. But what I'm going to do is activate two states at once. So we'll have two separate threads happening in parallel. See, I can't even stop thinking about the implementation of it. Then we can see what happens. In this case, we reach the end of the string, and since one of our states is successful, we can call that a match. In the case where it's not the end of the string, S4 has nowhere to go, so always fails and we discard it and let the other one continue. This is pretty cool, and you'll see later that it's pretty convenient for us when we want to construct finite automata out of regular expressions. However, one of the most important facts about the field of finite automata is that non-deterministic finite automata and deterministic finite automata have equal power. An NDFA can always be translated into a DFA that does the same thing. I'm not going to explore this in depth here, but here's an intuition for you. This non-deterministic finite automata can exist in a finite number of states. Let's say S2 and S4 are active at once. If S2 and S4 are active at once and we see an A, we know that S4 is going to die off and the next state to be active is going to be S3. What this means is that we could, in theory, make a big list of all the possible states of this non-deterministic finite automata, all the possible transitions from those states, and all of the next states after those transitions. This then is a deterministic finite automata, modeling the states of a non-deterministic finite automata. It's a pretty neat trick, and it's quite useful for optimization when you're building the engines. Anyway, as fascinating as that is, I'm going to move us on. Here is the roughly equivalent regex for this automata. You can see the plus operator can be used to signify repeating a group one or more times. We're starting to build up quite a powerful language here. We can think of finite automata as a kind of conceptual computer. There are certain things they can compute, like whether a string matches a certain kind of pattern, but they are limited compared to ordinary computers. One of the more advanced things they can do is compute whether a string has an even number of a particular character in it or not. Here's a regular expression that can do that with A's surrounded by H's. I thought I'd try hand converting this into a finite automata, and this is what I came up with. I thought this was pretty cool, and it seems to work, but once I'd stared at it for long enough, I started to suspect that there were quite a few redundant elements. So I ended up progressively eliminating them, and I ended up with this. Having done this, I realized that the core behavior of the underlying finite automata, both the last big one and this small one, is that it must take an even number of A's to get from one success state to another, and that every state should be able to absorb H's. Then I realized that even this could be simplified, and I ended up with this. At this level, the correctness is, I believe, easy to see. We start off in S1 as a success state with 0 A's in the string. This state, S1, signifies even. If we see an A, we leave that state, entering an odd state, until we see another A, making it an even state again. And at any point, we can accept H's which don't change the state. I find this very charming. It makes me think of Lionel Hutz with that smoking monkey.
He's taking another puff!
So finite automata are a very cute model of computation. Playing with them directly to figure out what they can do is pretty fun, but they are limited. They can't compute, for example, whether a string is a palindrome, the same forward or backwards. An intuition for this is that if they could match palindromes, then they would need to do it by keeping track of the first half of the string and comparing it to the second half, reversed. The first half of the string could in theory be infinitely long, and this would require an infinite number of states to store that information. That means it couldn't be a finite automata, so it's a contradiction. You could restrict yourself to strings of a specific length, but making a finite automata to match those would be an arduous brute force affair of matching all the possible strings of that length individually, so they're not really an appropriate tool. So a finite automata can recognize only certain kinds of patterns. In automata theory, the category of strings that a pattern matches is called a language. So let's say you have a pattern that's up to 4 A's followed by 5 B's. If you manage to make a list of all the strings that could match that pattern, you would call that list a language. You could also have an infinite language if you had any number of A's followed by 5 B's. All of this is in theory, of course. We can't make infinite lists in real life. So when we use the term language in automata theory, just imagine a set of strings that the pattern can recognize. We can categorize kinds of language too. A man named Noam Chomsky, who's a linguist amongst other things, created a hierarchy of languages called the Chomsky hierarchy. It starts out with languages which have a bunch of restrictions on them and then goes up to the least restricted. The least restricted kind of language is called recursively enumerable and can only be recognized by a Turing machine or something equivalent. The most restricted kind of language is called a regular language and can be recognized by a finite state automaton. Regular expressions in mathematics are just a convenient way of writing finite automata. They're called regular expressions because they can recognize regular languages. They were actually originally devised by a mathematician named Stephen Cole Kleiner. Oh, so close, so close. I really thought I got it. It's Kleiner. Kleiner, not Kleiner. It's Kleiner, okay? I'm going to say Kleiner for the rest of the video, so I really need you to know it's Kleiner. So keep that in your mind, Kleiner. In 1951. Kleiner also, like Turing, studied under Alonzo Church. Kleiner came up with regular expressions in a rather curious way. The summary of his paper proposing the idea begins with 2 questions. To what kind of events can a McCulloch-Pitts nerve net respond by firing a certain neuron? More generally, to what kinds of events can any finite automaton respond by assuming one of certain states? And the introduction begins, an organism or robot receives certain stimuli via its sensory receptor organs and performs certain actions via its effector organs. To say that certain actions are a response to certain stimuli means, in the simplest case, that the actions are performed when those stimuli occur and not when they do not occur. That's right. Kleiner was actually working on what we would now recognize as AI, and pretty interesting AI. How mechanical and biological systems respond intelligently to sequences of events over time. Look again at those finite automata. Don't you think they bear a certain resemblance to neural network diagrams? I can see it for sure, and recognizing patterns feels pretty AI-y. Just instead of events in time, like Kleiner was talking about, a computer scientist repurposed them in the 60s to search through sequences of strings in a text editor called QED. This, to me, is a fantastic example of the interplay between mathematics and computing. Of course, for there to be that interplay, we need to take these ideas from mathematics and figure out a way to compute them in practice. So let's do that. We're going to use an algorithm called Thompson's construction. It's named after the American Ken Thompson, who developed it while porting a text editor called QED and published it in 1968. Around the same time, Thompson was also working on designing and implementing the first Unix operating system, as well as producing a programming language called B, which would later inspire the programming language C. He's also one of the co-designers of the Go programming language. Now, as is common in this era, Thompson wasn't the only person working along similar lines. The algorithm we'll look at today is also sometimes known as the McNaughton-Yamada-Thompson algorithm. The Japanese Hisao Yamada, at the time a graduate student at the University of Pennsylvania, worked with his professor Robert McNaughton in developing and publishing an algorithm which could convert regular expressions to finite automata. This was published in 1960. However, I believe their algorithm is a little different to Thompson's algorithm. In fact, their algorithm in some ways is better. I believe it goes directly from regular expressions to deterministic finite automata, and so in theory would be more efficient. However, I haven't actually managed to get a hold of the original paper, which is called Regular Expressions and State Graphs for Automata. So if you can help me out, let me know. As a side note, later as a professor at the University of Tokyo, Hiso Yamada would be influential in solving the problem of how to create an ergonomic keyboard layout for Japanese writing. Anyway, that's probably enough history for now. Let's talk about the algorithm. We're not going to get quite as far as going from a string of regex characters to a... I just caught myself saying regex with a soft G. I'm never going to hear the end of this. Regex characters to a full working matcher. I'll just repeat that again. We're not going to get quite as far as going from a string of regex characters to a full working matcher. Instead, we'll skip the parsing part and focus on generating the finite automata by calling functions. In probably the video after next, we'll get into parsing itself. I'm going to use Python here, but I'll try to avoid anything too weird, and at the end I'll show you an example of how we can take this to a lower level too. Before we get into Thompson's construction, we'll need to decide how to represent our graph, that is our finite automata. I'm going to have a state class which does nothing at all. Its purpose is just so that we can create unique states without having to name them or give them special numbers or whatever. Next, we'll create a rule class. This represents a transition from one state to another based on some kind of rule. It has a start and an end state representing the state before and the state after. It will also have a matcher. The type here might look a little funny. Basically, it's just a lambda or a first class function which should take a character and return true if it matches or false if it doesn't. The match method just calls this matcher and returns the value. We'll see some examples of these soon. We also have a method called isEpsilon, which checks if this is what's called an epsilon transition. An epsilon transition is a transition which is followed automatically. Doesn't match any characters and doesn't move the pointer in the string along at all. You don't strictly need these for any finite automata or regex to work, but most algorithms use them because they make the process an awful lot easier, and you'll see why soon. We'll represent these with this little weird E here, which is the Greek epsilon symbol. Then we have our graph class, which has its own start and end. These represent the initial state highlighted here in white and our goal or matching state highlighted in green, sometimes also known as the final or accepting state. It then has a list of rules which are instances of the class we saw before. We also give it a label just for our own convenience if we want to print it out or whatever. Thompson's construction works by taking smaller graphs which represent small simple transitions and joining them together using special rules and often epsilon transitions. I'm going to go through a few examples and you can see them build up. We're going to implement this algorithm by creating functions which create graphs. Here's our first one, singleChar, which takes a character and returns a finite automata which matches a single character. It works by creating two states, start and end, which we've called here S1 and S2. It then returns a graph with these two states as the start and end states, along with the character itself as the human-friendly label. It then only has one rule, joining the start and the end states with a transition which should be followed if the character we see matches the character we've been told to look for. If that syntax looks weird to you, it's totally fine, I understand. All matchEQ does is take a character, which I'm going to call X, and returns a second function which will then return true if you give it the same character it was asked to look for, that's character X. You can see at the bottom that if we grab the rule out of the graph and call match on it, it will return true if given the character H, the one we originally passed to singleChar, and false otherwise. Let's look at another example. This one is very similar to singleChar. It's called anyChar and it matches any character at all. It's just like the dot character in a normal regex. Those special characters in regex, by the way, are called meta characters. The only difference between this one and singleChar is the matcher, which is now matchAny, which returns a function which always returns true no matter what character you give it. Now let's crank up the complexity a little bit. This is the asterisk meta character in regex and it means repeat the preceding item 0 or more times. So if we have an H and we put an asterisk after it, then it means the regex should match either an empty string, that's 0 repetitions, or 1H, or 2H's, or 3, or however many more. It's also known as the Kleiner star. after the guy I mentioned before who came up with regular expressions based on his explorations of neural networks. Now this function is a bit more sophisticated. It doesn't take a character as an argument, but instead takes a graph which we'll call the subject. That graph represents whatever is supposed to be repeated. We then create a new graph based on the subject graph. First, we include all the rules from the subject graph. Then we add 2 states and 4 more transitions. We add 1 transition from our start state directly to our end state. This lets us have 0 repetitions by skipping the subgraph entirely. We add 1 rule that goes from our start to the start of the subject graph. This lets us transition into that subject. We then add a rule from the subject's end to our end, which lets us transition out of it. Finally, we add a transition from the subject's end to the subject's start, which allows for repetition. Crucially, these transitions are all epsilon transitions. That means they don't absorb any characters or require any matching. For this reason, we set epsilon as a global constant and define it as a lambda function which always returns false. This means that when we write our execution algorithm later, we can treat epsilon transitions separately and assume that they will never match if we're looking for normal transitions that consume a character. You'll see all this in action later. For now, let's run this finite automata and see how it works. We start at P1 and then immediately follow both epsilon transitions to activate S1 and P2. If this was an empty string, we'd be able to mark it as a match because P2 is active. However, since it isn't, we consume a character. We look for the next transition and we find that P2 has nowhere to go, so we fail that state. S1, however, transitions to S2. It then immediately follows the epsilon transitions to P1 and S1. Again, this means if the string stopped here, it would be a match. But since it doesn't, we consume another character and the same thing happens. We loop around once more and now we're at the end of our string. One of our states is a success state, so we know there is a successful match. Here's another important operation, concatenation. For example, in the regex AB that matches A followed by B, we're talking about the followed by bit. Concatenation is implied in regex syntax, so there's no meta character for it as such. But as people implement in the algorithm, we don't get concatenation for free. We still need to find a way of joining graphs together. Fortunately, it's pretty easy. We just create a new graph with all the rules of the left and right graph and then add an epsilon transition from the end of the left graph to the start of the right graph. Now let's bring these things together and we can see the power of this algorithm. Here we're going to do something relatively advanced. Repeat a group of characters 0 or more times. This graph should match an empty string or the string AB or the string ABABAB, but not ABB or ABA. Let's see how it builds up. First, we add our graph for A, then our graph for B. Then we concatenate them. Then we apply the Kleiner star to repeat it 0 or more times. I've folded it up a bit here to make it easier to see, but it's the same thing. Notice how the operations that take graphs, like a concat or 0 or more, don't need to care what's going on inside the graphs they take as arguments. They just glue themselves on to the start and end states. We're going to see it now in action, and for this I'm going to show you the evaluation code too. We're going to focus first on the match method, which takes a string and returns true or false, indicating whether the whole string matched or not. Our starting state is the graph starting state, Q1. We immediately execute a helper method, follow epsilons on that starting state. This method finds all the states we could reach if we followed the epsilon transitions from a given starting state. The sharp-eyed amongst you may have noticed that it also includes the starting state, and indeed it actually returns all states that could be active even if we didn't follow every epsilon we could. This behavior becomes important in some situations, notably at the end of some executions where we want to know if a success state has been visited at all in the current iteration, or if we ever have a node which has an edge to an epsilon and an edge also to one that consumes a character. But this behavior isn't relevant in this execution, so I'm not going to reflect it in the visualization. So I'll be deactivating Q1 immediately, but at least you know that this is an important part of the behavior. Once we've resolved the epsilons in our starting state, we're ready to start going through the characters in our string, which we do one by one. We create a set to store the next states that we'll be moving to. If you don't know what a set is, then just for now imagine it like a list that automatically removes any duplicates you add to it. After this, we go through every rule that matches one of our states and the character that we've got. You could of course do this more efficiently if you indexed the rules by starting node or did something like that. All of this gets us one matching transition, the one from S1 to S2, which matches on an A. We call follow epsilons again to resolve those and get our new state, P1. Then we combine all of this into our next state set, and at the end we replace states with next states. Any states which didn't have rules matching don't get into the next states, and so they die at this point. And that's essentially it. We move on to the next character and go through the same routine. It's really beautiful to me that you can get quite complex pattern matching behavior out of a relatively simple process. I quite enjoy watching it. At the end, we check whether we can find the graph's end state in our list of active states, and if we can, then we've got a match. So Thompson's construction is the process of turning regular expressions into non-deterministic finite automata by sticking together smaller graphs to make bigger ones using epsilon transitions. You can look up the rules for different meta characters too, and I'll include some useful links for this on the ODE's website. Thompson's construction is not this execution algorithm here. Once you've got the non-deterministic finite automata, there are a few different ways you can apply it. Here I've taken the approach of simulating the non-deterministic finite automata by following each possible transition simultaneously. There are some other ways you can approach it though. Ken Thompson, for example, was implementing his algorithms in the 60s, and so he decided to compile his non-deterministic finite automata into machine code on the fly. Remember, he was making a text editor, so you would type your regex into the search, it would be compiled into machine code in the process, and then run over the text. Pretty cool. I was inspired by his approach to write this ARM64 assembly version of the deterministic finite automata we saw earlier. Really understanding finite automata conceptually will allow you to see that you can implement them in many different ways. Here, the state is being stored implicitly by the instruction pointer, and jumps are being used to execute state transitions. If you're feeling nefarious, you could also upstep Dijkstra by implementing this kind of algorithm with gotos in C. Now, this is a deterministic finite automata, but you can take a similar approach with non-deterministic finite automata too. Or you can use one of the algorithms that convert non-deterministic finite automata to deterministic finite automata, and if you implement those, you can make your execution simpler and more efficient. And there's quite a bit more I want to tell you about how programmers took this elegant abstract idea and twisted it into an even more useful form, about backtracking and about back references and why some people hate them so much. But that'll have to be for the next video. As for this one, this, like every ODE's video, has a page on the ODE's website with resources and exercises to get you putting this stuff into practice yourself. I've included a list of key resources, including the papers that I referenced in this video, as well as a few others, and the working Python and assembly code from this video. Now to the exercises. The first one, of course, is for you to build your own finite automata-based regex engine. You can either build on the Python one that I provided, or you can build your own from scratch in whatever language you would like. The second exercise flips regular expressions on their head. Instead of using them to match strings, you can also use them to generate strings. This may also help you get inside your head the idea of regular expressions as a grammar that describes a language. And I realize that I didn't use the word grammar in this video, so just wherever I say grammar, imagine pattern. We can use the pattern not just to decide whether a string matches that pattern, but also to generate strings that match that pattern. And the final exercise is a members only exercise and represents my thanks and appreciation for all of you who support me to make these videos. It's related to the assembly version we saw earlier, and I think you can have quite a lot of fun with it. And if you're wondering why it's been a bit longer since my last video, it's because I was working on the members conclusion project for the last chapter. This is an extended project where you build your own disassembler. And let me tell you, I learned an awful lot when I was putting that project together. So if you're interested in that and you want to become an ODE's member, you can go on the website and you'll find various things that will show you the way towards becoming a member. That's it for today. I'm acutely aware, actually, on the way back from the gym earlier, by the way, I think I can now deadlift a letter F, uppercase, obviously. On the way back from the gym today, I realized that does this video actually tell you how to create regular expressions, how to implement regular expressions at all? Or is it purely about finite automata? Anyway, the next video will be covering the other half of what we covered today. So going from strings all the way through to a working matching program, as well as a few other things about back referencing. Took me a few times to say that, and a bit of the other history and controversy and stuff like that. So that should be pretty fun. See you then.